I welcome you all in our today's session. Okay, in this session we are going to discuss about the steps to design the digital filter using impulse invariance method. In our previous video we have seen the equation by using the impulse invariance method for the digital filter. Okay, so in that case we have designed the equation, or we have derived the equation of h of z, which is equivalent to summation from k is equal to 1 to n, okay, ck divided by 1 minus e raised to pk into t, okay, z raised to minus 1, okay, which is derived from the analog system function, which is equivalent to summation from k is equal to 1 to n ck divided by s minus pk. Okay, now here in this case we are going to consider the steps to design the digital filter. Okay, so what are the different steps here? Okay, let us see. Okay, our first step is, for the given specifications, find firstly HA of S, okay, which is nothing but the transfer function of an analog filter. Okay, so we know how to find out HA of S. In our previous video we have seen how to design an analog filter. So firstly we have to find out the HA of S for the analog filter using those steps. Okay, now select the sampling rate of digital filter. Okay, t seconds per sample. Okay, this is our second step where we have to select the sampling rate. Okay, now if it is given, we have to choose that one. If it is not given, then we have to consider or assume the value of sampling rate. Okay, now express the analog filter transfer function as the sum of single pole filter. Okay, so we have to firstly find out the HA of S in term of summation of single pole filter. Okay, so it is k is equal to 1 to n ck divided by s minus pk. Okay, so we have to find out the system function here. Okay, then compute the Z transform of the digital filter. By using the formula h of z is equivalent to summation from k is equal to 1 to n ck divided by 1 minus e raised to pk into t z raised to minus 1. Okay, so this is the case when the sampling rate is low. Okay, so for high sampling rates, we have to use the equation h of z is equivalent to summation from k is equal to 1 to n ck multiplied by t divided by 1 minus e raised to pk into t z raised to minus 1. That means we have to just multiply the equation of h of z by t here. Okay, for high sampling rates. If it is low, then no problem, we have to consider this equation only. Okay, so these are the different steps to design the digital filter using impulse invariance method. Okay, so only 4 steps are included here. Okay, so first step is, for a given specification, we have to find out the transfer function of the analog filter. Then we have to consider, or we have to choose the appropriate sampling rate of the digital filter. Okay, we have to express our analog filter transfer function in terms of a sum of single pole filter, that is in terms of HA of S is equal to summation from K is equal to N 1 to N Ck divided by S minus Pk. That means we have to just find out the poles and coefficients here. Okay, then we have to compute the Z transform of the digital filter by using this formula. The Ck and Pk that we have derived from the earlier step, okay, we have to replace here and we have to find out the H of Z value. Okay, so we will consider one example of this impulse invariance method. So we will get an idea how to design any digital filter using impulse invariant method. Okay, so here we will consider the analog transfer function H of S, which is equivalent to 2 divided by S plus 1 into S plus 2. Okay, so this is the analog transfer function H of S. Okay, now we have to determine the H of Z, okay, using the impulse invariant method. Okay, we will assume here that T is equivalent to 1 second. Okay, this is the sampling rate. Okay, so here analog transfer function is provided. Okay, and we have to find out H of Z here. Okay, so what is given here? Given is H of S is equivalent to 2 divided by S plus 1 into S plus 2. Okay, so here we have to use the partial fraction method so that our equation or our transfer function gets converted in terms of sums of the poles, okay, single poles. Okay, so here we use the partial fraction method. So H of S now becomes A divided by S plus 1 plus B divided by S plus 2 here. Okay, now we have to find out the values of A and B. Okay, so what is A here in terms of partial fraction method? Okay, it is nothing but S plus 1 multiplied by 2 divided by S plus 1 into S plus 2, okay, at S is equivalent to minus 1. Okay, so substituting these values and solving for S is equal to minus 1, this will become 2 divided by S plus 2, which is equal to 2 divided by minus 1 plus 2. Okay, so this value is equivalent to 2. Okay, so here the value of A is equivalent to 2 in our case. Now how to find out B? B is equivalent to now S plus 2 multiplied by 2 divided by S plus 1 into S plus 2, okay, at S is equivalent to minus 2. So here solving this equation for S is equivalent to minus 2, it will become minus 2 plus 1, which is nothing but minus 2. So the value of B is equivalent to minus 2. Now replace this value of A and B in our equation of H of S in terms of A and B. So what is our equation of H of S? H of S becomes now 2 divided by S plus 1 plus minus 2 divided by S plus 2. Okay, so here our equation becomes 2 divided by S minus minus 1 minus 2 divided by S minus minus 2. Okay, so this is the equation of H of S. Okay, now what we have to do? We have to compare this equation with H of S Okay, HA of S is equivalent to summation from K is equivalent to 1 to N Ck divided by S minus Pk. Okay, so here our equation of H of S is equal to 2 divided by S minus 1 plus, minus 2 divided by S minus 2. Okay, we have derived it. Okay, so here what are the values of poles and the coefficients we are going to find out. Okay, so in this case, okay, what is C1? C1 is equivalent to 2. What is C2? C2 is equivalent to minus 2. Okay, and what is P1 now? P1 is equivalent to minus 1 and P2 is equivalent to again minus 2. Okay, so this is our P2. Okay, now what we have to do? We have to substitute the values of Ck and Pk in the equation of H of Z now. So what is our H of Z? Okay, so it is equivalent to K equal to 1 to N Ck divided by 1 minus e raised to Pk t into Z raised to minus 1. So replace the values here. So what is H of Z then? H of Z becomes, what is our C1? So in this case 2 coefficients and 2 poles are there. So it is C1 divided by 1 minus e raised to P1t Z raised to minus 1 plus C2 divided by 1 minus e raised to P2 into t to Z raised to minus 1. Replace the values of C1, C2 and P1, P2. So our equation now becomes 2 divided by 1 minus e raised to P1 is minus 1. So minus 1 into t Z raised to minus 1. So C2 is minus 2. So it is minus 2 divided by 1 minus e raised to P2 is again minus 2. So minus 2t Z raised to minus 1. Okay. Again here t is given, that is 1 second. So the final equation for H of Z is equivalent to 2 divided by 1 minus e raised to minus 1 into Z raised to minus 1 minus 2 divided by 1 minus e raised to minus 2 into Z raised to minus 1. Okay, so after simplifying this, okay, what is H of Z? H of Z becomes 2 divided by 1 minus the value of e raised to minus 1 is 0.3678 Z raised to minus 1 minus 2 divided by 1 minus 0.1353 Z raised to minus 1. Okay. So again after simplification we have H of Z is equivalent to 0.465 Z inverse divided by 1 minus 0.503 Z inverse plus 0.04976 Z raised to minus 2. Okay, so this is the equation for digital filter. Okay, so thus from the analog filter we have derived the equation for the digital filter. Okay, so using the impulse invariance method. Okay, so we will see one more example so that we will get the clear idea for the impulse invariant method. Okay, so let us consider here the H of S is equivalent to 1 divided by S square plus square root of 2 into S plus 1. Okay, and the t is given, that is equivalent to 1, and we have to determine again H of Z. Okay, now in this case the H of S is provided for the analog filter. Okay, now here consider H of S is equal to 1 divided by S square plus square root of 2 into S plus 1. Okay, so we have to find out the H of t now. So H of t is nothing but the L inverse of H of S. Okay, which is nothing but the L inverse of 1 divided by S square plus square root of 2S plus 1. Okay, so it will be L inverse of or inverse Laplace transform of 1 divided by s plus 1 square root of 2 bracket square plus 1 divided by square root of 2 of bracket square. Okay, so here it will become L inverse of square root of 2 into 1 divided by square root of 2 divided by s plus 1 divided by square root of 2 square plus 1 divided by square root of 2 square. Just we have multiplied and divided by square root of 2 here. Okay, so take this square root of 2 outside. So it is square root of 2 L inverse of 1 divided by square root of 2 divided by s plus 1 divided by square root of 2 bracket square plus 1 by square root of 2 of bracket square. Okay, so this is equivalent to square root of 2 into e raised to minus t divided by square root of 2 into sine t by square root of 2 by taking the inverse Laplace transform. Now here let t is equivalent to nt. So h of nt then becomes equivalent to square root of 2 e raised to minus nt by 2 into square root of 2. So it will be again square root of 2. Okay, sine nt divided by square root of 2. Okay, so at t is equivalent to 1 second, we have h of n is equal to square root of 2 into e raised to minus n by square root of 2 sine of n divided by root 2. Okay, so here by converting this equation into h of z, okay, we have square root of 2 into e raised to minus 1 divided by square root of 2 into sine 1 by square root of 2. The whole divided by 1 minus 2 into e raised to minus 1 by square root of 2 z raised to minus 1 cos of 1 by square root of 2 plus e raised to minus square root of 2 z raised to minus 2. Okay, so after simplification we have okay 0.453 z inverse divided by 1 minus 0.7497 z inverse plus 0.2432 z raised to minus 2. Okay, so in this way, okay, there are two different ways we have seen to solve or to convert the digital filter into the analog to convert the analog filter into the digital filter by using the impulse invariance method. Okay, so first one is the partial fraction method, and by second method can consider the conversion of analog filter into the digital filter. Okay, so here we have considered the 4 steps. Which are those 4 steps? We will revise once again. Okay, so for the given specification, if HA of S is not given, we have to find out the HA of S. Then we have to select the sampling rate of the digital filter. If it is not given, then we have to assume it is equal to 1 second. Then express the analog transfer function, okay, in the form of the sum of single pole filters, that is HA of S is equivalent to summation from k is equal to 1 to n Ck divided by S minus Pk. And then lastly we have to compute the Z transform of the digital filter by using the formula H of Z is equal to summation from k is equal to 1 to n Ck divided by 1 minus e raised to Pkt into Z raised to minus 1. Okay, and for high sampling rate, just we have to multiply the equation by t. Okay, so this is the simplest method to convert any analog filter into the digital filter. Okay, I hope okay you all are now able to convert the analog filter into the digital filter by using the impulse invariant method. Thank you.